Hey everyone, welcome back to linear algebra. This will be lecture 11 of the course. And in this section, we're going to discuss some of the additional properties of determinants. In the last section, we introduced what the determinant was, the last two sections, and discussed some of the properties of determinants, some of the value, the usefulness of them. And in this section, we're going to expand on that list. And some of the stuff that we'll discuss in this section in particular are pretty remarkable. So we're going to discuss specifically a couple of things. Let's jump into it. First, we're going to get into the determinant of a product. All right, so what is the determinant of a product of two matrices? And we'll then discuss the determinant of a transpose. Okay, so if I transpose a matrix, what is the determinant of the matrix in relation to the determinant of A itself? And then we'll also introduce a concept, a matrix called the adjoint. And this is this is a topic that a lot of people get lost on. Hopefully we can make it kind of clear what's going on here, but it's a pretty remarkable properties of the adjoint and the determinant. And then finally we'll briefly explore an alternative method for solving systems using the determinant. This is a method called Cramer's rule. And it's for solving systems. Okay, yeah, so that's kind of what we're up to in this one. Again, a little bit of a mix of ideas, but all kind of centered around the idea of determinants. Okay, all right, so the first thing we want to talk through is what happens to the determinant of when we multiply matrices. Okay, and so this one couldn't be any more convenient. Basically, if A and B are n by n matrices, then the determinant of the product is equal to the product of the determinants. Okay, so the determinant of AB is equal to the determinant of A times the determinant of B. So, as I say, it doesn't get much nicer than that. That's about as nice as you can. It's about as much as you can hope for. And I mean, I think if you look at this and you think about how the determinant's calculated, using cofactor expansions along rows, it may not be obvious why this would be the case. And indeed, it is not totally obvious. So let's go ahead and actually we won't prove everything in this lecture, but let's prove this one. This will be one of the more challenging proofs we've seen. Well, yeah, I'd say it is reasonably challenging. So we're going to consider some cases, and the first case we're going to consider is the first handful of cases is where A is a singular matrix. Okay, so we're going to assume that A is singular to start with. Okay. Now, if A is singular, that implies that the determinant of A is equal to 0. Okay, we saw that in prior theorems. Right, and so if the determinant of AB is also 0, we're done. Okay, if that's the case, we're done. So let's suppose instead that the determinant of the product is non-zero, and we'll prove a contradiction. Okay, we'll derive a contradiction. All right, so we're assuming A is singular, which implies that the determinant is 0. And now we're going to assume that the determinant of the product is somehow non-zero. Okay? And so let's see what happens. So if the product has a non-zero determinant, well, then that implies that there's an inverse. Okay, we saw that earlier. So that implies that an inverse exists. Okay, and specifically, we'd be able to say that A times B, that product matrix, is gonna, if we multiply by whatever AB inverse happens to be, that's going to be equal to the identity. Okay, right. And so this is just, I mean, these are the consequences of the determinant being non-zero, right? So non-zero determinant means you have an inverse, which means this relationship exists, right? So let's just use this and see what we can see. So if I have the identity equal to AB times AB inverse, I can reassociate this, right? This is the same thing as, I just think of A as being by itself, and then B times AB inverse, like so. Then what does this imply? Well, I've got a matrix here, A, and I've got another matrix here, B times AB inverse. And that product is equal to the identity. Well, so what this implies is that B AB inverse is an inverse. This matrix here is an inverse of A. Right? Because, I mean, what do I see here? I see that A times B AB inverse is equal to the identity, right? So this is at least a right inverse. Okay, and so that's a problem, right? Why is that a problem? That implies a contradiction because we assumed A is singular. If A is singular, then it does not have an inverse, right? So this BA, B inverse matrix here shouldn't exist if A is singular, right? So that's a contradiction, okay? So in the case of A being a singular matrix with a zero determinant, we can see now that the determinant of A times any other matrix has to be non-zero, has to be zero as well, okay? So what have we shown? So A equal to 0, A singular implies AB equals 0, and B doesn't matter in this scenario. Okay, so that's the first big case we want to look at. Okay, we'll assume next the case where A is non-singular, where, i.e., there is an inverse for A, and A is going to have a non-zero determinant. Okay, so we'll assume secondarily that A is non-singular. Okay, A is now non-singular. And then there's a subcase here that we can get rid of really quickly. So let's consider the case where A is the identity matrix. All right, so A equals IN. Okay, that implies what? Well, that implies that the determinant is 1, and we can quickly show, right? So say we start with the determinant of AB. Well, if A is I, then this is the determinant of I times B, right? Which is equal to just the determinant of B, right? Because I times B is just B, right? And so this is, of course, equal to 1 times the determinant of B, which is the determinant of A times the determinant of B. Okay, so it works out fine if A is the identity matrix. Yeah, this is sort of the trivial, more kind of trivial case, right? This is not the interesting case. Okay, but we should consider it. Obviously, we have to consider it. Okay, so then let's assume, again, holding A to be non-singular, let's consider the case where A is not the identity matrix. So again, A is non-singular, and A is not equal to the identity matrix. Basically, this means that A is any other matrix with an inverse. Okay. Okay, so A non-singular, right? We're assuming A is not equal to the identity. It isn't the identity matrix itself, but if A is non-singular, then it's row equivalent to the identity matrix. So A is row equivalent to the identity matrix. And what does that mean? Well, it means that I can apply some series of row operations to the matrix A and reduce it to the identity matrix. So A can be row reduced to the identity matrix. Okay, so this implies that there exists R1, R2, dot, 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 RK, however many there may be, row operations, such that normally we think about applying the row operations to A, but remember, row operations are all reversible. So if I know what row operations can be applied to A to get to the identity, then I can just take the inverse operations and apply them to the identity to get to A. And so that's what we're going to do here. We're going to say I've got a row operation K minus 1, dot, 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 all the way down to row operation 2, row operation 1. And if I apply that to the identity matrix, that's going to be equal to A, right? So I can take the identity matrix and I can convert it into A using row operations. That's what it means for A to be row equivalent to the identity. Okay, and again, remember, these are the inverse row ops that take A to IN. Okay, all we need to understand, we don't care what they are, just so long as we know that it's possible to do this. Okay, and now if you recall, when we were talking about, in the last section, we talked about the determinant in relation to row operations. And we said that basically for each row operation, for each Ri row operation, there's some real number that we have to apply to the determinant. So for each Ri, there is an associated real number, little ri I'll call it, right? So for each Ri, there is an associated real number, little ri, so that applying row operation Ri to a matrix multiplies its determinant by Ri. Little ri. Okay. So remember that? That was the main gist of the previous lecture, right? Was that these row operations impact the determinant, but it's possible to keep track of the impact to the determinant. Okay, so if this is the case, then I'm going to use that to figure out what the determinant of AB is. So if I start with AB, okay, now we just showed that this A can be written as a nested series of row operations on the identity matrix. So let's replace A with this right here. Okay, instead of A, we're going to replace it with this part, this guy up here. Okay, so that means we've got the determinant of AB is equal to the determinant of the row operation K, dot, 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 R2, R1, times the identity, times B, like so. Okay, so this is again just A. All right, no problem. And there's a theorem that we had earlier in the course that said it was possible to move matrices inside of row operations like this. And so this is really RK dot 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 R2 R1 times the identity times B. Okay, now where does this come from? So remember, the theorem was something like this. It said if I have a row operation on the matrix AB, then that's equal to the row operation on A times the matrix B, right? So I can move the matrix inside this row operation or conversely outside. Okay, and we said when we talked about this that you could do this for not just one row operation, but you could sequential operations, mini. And that's what we're doing here. Okay, so that's from a previous section. This was from the section on row reduction. We talked about that back in the row reduction section. Okay, and we just talked about how each of these row operations, from the standpoint of the determinant, is basically equivalent to multiplication by some real number, right? So we'll represent that using these little r's. So rk dot 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 r2 r1 times the identity times the determinant of the identity matrix times b. Okay. And it's very important to keep in mind what these numbers are. So remember, row operation 1 was multiplication by a scalar. So in that case, these numbers are going to be that whatever scalar you multiply by. For row operation 2, which was replacement of a row by a scalar multiple of a previous row plus the given row, there we got it for free. So in those cases, these would all be 1. And then interchanging rows resulted in multiplication by -1, right? So flipping of the sign. So these are all, that's where these numbers come from. This is nothing mysterious. It's just we're using it in a very sort of abstract way here. All right, so we get down to this, which is just a series of real numbers times a determinant. Okay, and this is clearly just rk dot dot dot, let me put on the next line, rk dot 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 r2 r1. Now here we can break this apart into the identity times b. Okay, and what can we do next? Well, the next thing is, since we've got the identity pulled apart here, we can plug all of this back in to recover a, right? All of these real numbers can be converted back into these row operations on the identity in order to recover the matrix A, right? And so this is going to be the same as rk dot 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 r2 r1 times the identity, right? And then times the determinant of b. All right, so all of this work here was just to get it down into this form so that we could break it apart, and then we can reassemble A just the same way we disassembled it. And so this is going to be equal to the determinant of A times the determinant of B. Okay, which is exactly what we want to show. Remember, we wanted to show that the determinant of the product is equal to the product of the determinants, and that's what we got to. Excellent. Okay, so this piece here, make sure that you understand this. This is a little bit of a trickier section. Make sure you are convinced of this. If you are having trouble remembering this discussion, you can go back, probably lecture 3 or 4 maybe, where we discussed this theorem in general. In general, yeah, we talked about this. We might have proved that. I can't recall. Okay. All right. Excellent. So that's pretty interesting, right? Let's do an example just to kind of see it with our own eyes. So let's let A equal 1, 2, 0, 3, and we'll let B equal 2, 3, 0, 4. Okay. Then we can multiply A and B together. So 1, 2, 0, 3 times 2, 3, 0, 4. And we get 2, 11, 0, and 12. Okay. Now, what are the determinants of all these matrices? Well, the determinant of A, we can look here, is 1 times 3. This is a diagonal. So the determinant's 3. What about the determinant of B? 2 times 4, again, diagonal. So it's 8. The determinant of AB, well, it's 2 times 12, 24. Right? And so here we can clearly see that AB, the determinant of AB is equal to the determinant of A times the determinant of B, right? Because 24 is equal to 3 times 8. So it checks out. Perfect. So it's just an example, practical example of this very elegant, very perfect relationship between the determinant of two matrices and the determinant of the matrix product. Exactly what you like to see. Okay. Another theorem. This one will be much quicker to show. It's almost a corollary of the previous one. So if A is non-singular, then the determinant of the inverse of A is equal to 1 over the determinant of A. That's interesting, right? So the determinant of the inverse is literally the reciprocal of the determinant of A. That's very kind of remarkable, I think. I mean, it really forces you to kind of think about these things, and there's a remarkable symmetry here to the kinds of things you would see with real numbers. So inverses of real numbers are reciprocals typically, and so you see kind of the same thing playing out here. If A is non-singular, then the determinant of A inverse is literally the reciprocal of A's determinant. Let's prove it. Proof is simple, one line. Well, maybe two lines. If A is non-singular, well, then you have this, right? A inverse equals the identity matrix. What does that mean? Well, so if I take the determinant of A inverse, the previous theorem showed us that that's the determinant of A times the determinant of A inverse. And we know that's equal to the determinant of the identity, which is 1. Okay, and so this is going to basically give you what you need here. These are real numbers, right? They're just numbers. So I can divide by the determinant of A. And so what I get is that the determinant of A inverse is equal to 1 over the determinant of A, right? So just doing this. So there, that's where that comes from. So very simple proof, but very, very nice result, clean result. All right, let's jump to a discussion of transpose. Let's talk about what happens with the transpose. Okay, if A is an n by n matrix, then the determinant of A is equal to the determinant of the transpose. Okay, so again, about as nice as you can hope for. Let's do an example here. I don't think we'll prove this one, just in the interest of time. But let's do an example. So let's let A equal 1, 0, 1, 0, 2, 3, 0, 0, 1. Okay. So we can, this is a upper diagonal, so we can see that the determinant here is equal to 2. 1 times 2 times 1 is 2. Okay, so that's the determinant. Now what we want to show is that the transpose has the same determinant. All right, so let's see what the transpose looks like. So if I transpose this matrix, I have 1, 0, 0, 0, 2, 0, 1, 3, 1, like so. And this is not a diagonal matrix, but I can use row operations to convert it into an upper diagonal matrix with relative ease. And so what I would do there is I could say, I can convert this into a 0, so I can do -1, bring that down. And when I do that, I get 1, 0, 0, 0, 2, 0, 0, 3, 1. Right, now what's the payment on the determinant for doing this with regard to the determinant? What do I have to pay? Well, I have to multiply the determinant by 1, right? This is the row operation type 2, which I actually get for free. It doesn't have any impact on the determinant. Okay. Next thing I need to do is I can convert this to a 1. Let's make that into a 1. And so I can multiply by 1/2. Okay. Multiply row 2 by 1/2. So I get 1 0 0 0 1 0 0 3 1. What's the payment here with regard to the determinant? Well, I have to multiply by 1/2, right? So I'll keep track of it up here. So I multiply by 1, and then multiply by 1/2. These are like the little r's, right? So this is like R1, this is like R2, little r, right? This is row operation 1, that's the determinant payment. Row operation 2, determinant payment. And I can do one more thing. I can multiply by -1 and add that, multiply row 2 by -1 and add that to row 3. When I do that, I actually get, this goes into precisely into the identity form, right? And so row operation 3, payment is a 1. Again, this is one we get for free. Okay, and so then this is just equal to the identity, I3. Right? And so I can set this up, and what this basically says is that 1 times 1/2 times 1 times the determinant of the transpose is equal to the determinant of I3, which is 1. Okay, and so I can do a little bit of algebra to this. Basically, I'm not interested in this piece anymore, but I want to know what the transpose determinant is. So that's equal to 1 divided by this, which is 1 times 1/2 times 1, which is just 1/2. And so I get 2. Okay, and so you can see here that the transpose has a determinant of 2. The original matrix also had a determinant of 2. Okay, and so actually with this matrix, we could very easily calculate the determinant using a cofactor expansion as well, right? I just kind of chose to do this because we talked about this recently, and it was literally this methodology was just used in the last proof, and so kind of bringing that in here is useful. Okay, excellent. Great, so now we know some more about the determinant. We know that the determinant of a product is equal to the product of the determinants. We know that the determinant of an inverse is equal to 1 over the determinant of the original matrix. Okay, so we know this one. And we've just done an example where we've shown, well, in this specific example, we haven't proven this yet, but we've shown that the determinant of A is equal to the determinant of its transpose. So that's 3 extremely nice results. You couldn't ask for nicer results there. And so now we're going to kind of shift gears for a second. And we want to talk about, we actually brought this up previously, but I want to state it formally. When we initially defined the determinant, we said that it's the cofactor expansion across the nth row. Okay, so initially we said that the determinant was the cofactor expansion across the nth row. Okay, so we said that initially. And then I did indicate when we were talking about that in fact you can, it's true that the determinant can be calculated using a cofactor expansion across any row and across any column. And we just want to explore that for a moment. And so let's state it formally. So let's let A be an n by n matrix. So A is an n by n matrix with n greater than or equal to 2. Then, 2 things. First, A is, the determinant can be calculated by doing a cofactor expansion across any row. So the way we would write that is the determinant of A is equal to A I1 times the cofactor I1, AI1, plus AI2 times the cofactor AI2, plus dot dot dot, plus AIN times the cofactor AIN. Okay, and this is for each I, 1 less than or equal to I less than or equal to n, right? So you fix I, choose whichever row you like, do a cofactor expansion across it, and you have the determinant. And what this basically says is that it doesn't matter which one you choose. You get the same answer for all of them, which is kind of remarkable. It's also true, you can do the same thing across the columns. So the way to kind of write that would be A1j times the cofactor A1j plus A2j times the cofactor A2j plus dot 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 plus ANJ times the cofactor ANJ. Okay, and this is for each j, 1 less than or equal to j less than or equal to n. Okay, so you can also do it across the columns. It works the same way. All right. So I think, we definitely mentioned this before, but let's, I don't think we elaborated on it. Let's go ahead and do a nice example showing this property. This is kind of remarkable. It hints at something very, kind of deep structure to matrices that you maybe don't notice right away. So let's let A equal 1, 0, 3, 2, 1, 4, 0, 0, 1. Okay, so you've got this matrix. So let's start. We're going to calculate the determinant of this thing using different rows and columns. So we'll start by using row 3. Let's use row 3 to start with. All right, so if we're using row 3, then the determinant of A is going to be, well, you got 0 and 0 for the first two cofactors. So 0 plus 0 plus. Then you got a 1, and then negative 1, and this is the 3, 3 position, so 3 plus 3. And then the submatrix is 1, 0, 2, 1. All right, so it kind of looks like that. So what do we have here? 0 plus 0 plus, this is 1 times 1. And then what do we have here? 1 minus 0. So we get a determinant of 1. Okay. Looks good. Let's use row 2. So let's move up a row. So I'll target the middle row this time. Okay. If we do it this way, the determinant of A is going to be, so again, here we have non-zero entries, right? So this one will be maybe slightly more involved than the previous, but so you're going to have 2 times negative 1 to the 2 plus 1 power, and then the submatrix will be 0, 3, 0, 1. Okay, so that's the first entry, and then it's 1 times negative 1 to the 2 plus 2 power, and the submatrix is 1, 3, 0, 1 plus, and then it's 4 times negative 1 to the 2 plus 3 power, and the submatrix is 1, 0, 0, 0. Okay, so let's see what happens here. So I've got a 2 times negative 1. This is going to be 0 minus 0. Okay, so that's all zeroed out. Here I've got a 1 times a 1, and then I got 1 minus 0. And then here I've got 4 times negative 1, and then 0 minus 0. Right, and so what do I have? I have 0 plus 1 plus 0. So I get the same answer for row 2. Okay, what about using row 1? Let's go up to the top row. Okay, the top row, Again, I've got two non-zero entries, so this will be kind of the intermediate level of complexity here. So the determinant of A is equal to 1 times -1 to the 1 plus 1 times 1, 4, 0, 1 submatrix plus 0, right? Entry 1, 2 is 0, so we can just put 0 there. We know it's going to be 0. And then plus 3 times -1 to the 1 plus 3 power, and then the submatrix is 2, 1, 0, 0. Okay, and we can go through this, and what do we get? We get 1, 1, and then 1. Well, 1 minus 0 here, but I just wrote 1. That's okay though. And then here I get 3, and then 1, and then 0 minus 0. Okay, so you can see that this is 1 plus 0 plus 0, so again 1. Okay, so we've shown that across all three rows, the cofactor expansion, totally different in each case, but yields the same value for the determinant. We won't do all the columns, but let's try the same exercise across column 2. So let me rewrite the matrix so it's on the screen here. Okay, so here we're going to use column 2. Just go down the middle here. And so doing it in that way, we would say it's equal to 0, right? So 0 is the entry along column 2. And I'll just put in the rest of it just so you can see how it would break down. So this would be row 1, column 2, so 1 plus 2. And then the submatrix is 2, 4, 0, 1. The cofactor expansion works the same along the columns. You just have to kind of shift the way you're indexing things if you're thinking about it in terms of, like the formula. Okay, and then the entry is 1, and then it's -1 times 2 plus 2, to the 2 plus 2 power. And then the submatrix is 1, 3, 0, 1. And then it's another 0 times -1 to the 3 plus 2 power. And then the submatrix is 1, 3, 2, 4. Okay. Right, and we can just go through this quickly, and we know that this is going to be 0 because I've got a 0 there. The middle one is where we're going to get something, and it's going to be 1 times 1 times 1 minus 0. And then the last one will be 0 as well. So you can see we get 1 as, once again. So we've done, so we've shown that, look, we've calculated the determinant using 4 different expansions. We went across row 1, then we went across row 2, then we went across row 3, then we went across column 2. And you can confirm on your own if you went across the other 2 columns, you would get the same answer. So that's very remarkable. That's an interesting feature, very interesting feature of the determinant. No matter how you do the cofactor expansion, you get the same answer. It doesn't have to be along the lower row as we had previously indicated. The lower row is just, where you start. Like when you're first learning about the determinant, because you don't want to overwhelm anybody, you've got to start with just fix a row, set up, get used to it on that row, and then realize, oh, it doesn't matter which row it is actually. And that's very convenient because, depending on the matrix, it may be easier or harder to calculate the determinant by doing cofactor expansion. So for example, if I have a matrix like this, like the one I just looked at, for example, in this case, probably going over row 3 is the fastest. Maybe column 2 could be just as quick. But if instead these were 8s, well, that's different. In this case, probably the fastest is to go across row 1, right? Or if that was a 0, then certainly row 1, right? You know what I mean? So like you can pick and choose. You find the row you find the row or column with the most zeros, and that's where you do your cofactor expansion. And so you can be a little bit strategic using this fact that the determinant can be calculated across any row or column. Okay. All right, very good. Let's talk next about a very interesting construct in linear algebra that is called the adjoint. So this is something that a lot of people find very confusing, and we'll try my best to make it as clear as possible. But let's start with the confusing definition. So let A be an n by n matrix. Okay, and we'll say with n greater than or equal to 2. Then and this is technically called the classical adjoint. The classical adjoint of A is the n by n matrix, right? So the adjoint is a matrix. It's the n by n matrix whose ij entry is cofactor ji. Okay, and this would be the cofactor ji of A. Okay. All right. So A is an n by n matrix, and what we're doing with the adjoint is we're taking all of the cofactors that would be used to calculate the determinant, and we're repopulating a matrix with those cofactors. Okay. So for example, back here, this is what we mean by, well, not that actually, just this part. This is one of the cofactors. This is the 1, 1 cofactor. This would be the 1, 3 cofactor, right? This was the 2, 1 cofactor. This is the 2, 2 cofactor. This is the 2, 3 cofactor. Okay, so let's talk this through. So let's start with an example. Let's write A11, A12, A13, A21, A22, A23, A31, A32, A33, right? So this is a matrix, 3 by 3 matrix, and we'll call this A. Okay, now the adjoint of this matrix would be the following, right? So the notation here is just a cursive script A with no subscripts. Okay, and so the adjoint here is going to be, again, a 3 by 3 matrix, but what's going to happen here is the A11 you would calculate like this, so it'd be A22, A23, A32, A33. Okay, and so you're going to calculate the determinant of that, and it's going to be positive. So where does that come from? Well, this is going to be a big matrix, right? So this is the 1, 1. And so basically you're going to block out there, and that becomes the adjoint positive, right? Now when I go to the next one, it's going to be a negative, and it's going to be basically blocking out the first row and the second column. So it'll be this one, this one, this one, and this one. So A21, A23, A31, A33. Right, and then the third one, you know, the 1, 3 entry of the adjoint is going to be obtained by blocking out these two. Okay, and so it's going to be a positive, right? Because 3 plus 1. Think of the negative 1 to the I plus j power. That's what's determining the signs here. And so it'll be A21, A22, A31, A32. Again, these are the determinants. So these are real numbers, right? I'm just kind of showing you the structure here. Okay, and then let's fill in the rest here. I'll just do it quickly. A12, A13, 32, 33. Okay, and in this one, this would be the 2, 1, so that's a negative. Then this one will be positive, and it'll be 1, 1, 1, 3, 3, 1, 3, 3. And then this one is negative again, 1, 1, 1, 2. A 2, 1, a 2, 2. Okay, and then finally down here for the last row, you'll have an A1, 2, A1, 3, A2, 2, A2, 3. And then negative, A1, 1, A1, 3, A2, 1, A2, 3, and finally the last one over here, A1, 1, A1, 2, and then A2, 1, A2, 2. Okay. All right, so this is the adjoint, but not quite actually. Not quite, because remember up here it says the classical adjoint of A is the n by n matrix whose ij entry is the ji cofactor, right? So actually this guy here, for example, should be down here. This one here should be down here. So this is not the adjoint, but this is the transpose of the adjoint, right? So the actual adjoint will have to be would be the transpose of this. Okay, so that's really interesting. That's really interesting, right? So remember, this is A1, 1 right here. This is A1, 2 right here. Here's A1, 3. Right? And so these all have to be transposed, right? So this guy should be down here, this one should be down here, and that's just the transpose operation. So I always recommend if you're asked to calculate the adjoint, just do it this way and then transpose the results. It's just a little bit easier to keep track of what goes where. Okay? And so in general, the adjoint will have the form A1, 1, adjoint 1, 1, adjoint 2, 1, adjoint n1, and then it's adjoint 1, 2, adjoint 2, 2, adjoint n2, and dot dot dot, adjoint 1n, adjoint 2n, adjoint nn. Okay, right, so remember, so here's your 1, 2 is here. Let me bring that up a little bit. But you can see that when we calculate it in the normal way and then transpose the results, right? So it's simple to do it. It's easier to calculate it this way first and then transpose it to get the true adjoint. Hopefully that makes sense. Let's do an example. Let's do a real example with some real numbers. Let's see what this looks like. It can feel like a very complicated process on the surface, but it's actually more redundant than complicated. So let's start with this matrix that we've worked with before. So 1, 0, 1, 0, 2, 3, 0, 0, 1, 3 by 3 matrix. So then the adjoint is going to be equal to, and this is going to be a little bit of a mess, but I'm just going to write it all out. So the first entry will be 2, 3, 0, 1. Positive, right? The determinant of the submatrix you get when you block out the first row, first column, 2, 3, 0, 1. The second entry is going to be the submatrix you get when you block out the first row in the second column, right? So that's going to be 0, 3, 0, 1. Okay, and then the third entry on the first row would be 0, 2, 0, 0. Okay, and then you move down and it's going to be negative 0, 1, 0, 1. And then it's positive 1, 1, 0, 1. And then it's negative 1, 0, 0, 0. And then it's positive 0, 1, 2, 3. And then it's negative 1, 0, 1, 3. And then it's positive 1, 0, 0, 2. Okay, and so this is the adjoint, but remember, we have to transpose it. Okay, and so we can quickly do this. Okay, so let's go ahead and push this through. So it'll be 2 minus 0, so I get a 2 up here. And then it'll be 0 minus 0, so 0 there, and then 0 minus 0 there as well. And then it'll be 0 minus 0, and then 1 minus 0, and then 0 minus 0, and then 0 minus 2. Okay, and then here you're going to have 3 minus 0, but it's negative, so it'll be negative 3 minus 0. And here I get a 2. Okay, so it looks like that. And then finally, doing the actual transpose, I get 2, 0, negative 2, 0, 1, negative 3, and then 0, 0, 2. Okay, so this is the adjoint of A. That's the adjoint. Okay, so that's how you calculate it. Got to go through all these submatrices, calculate the determinants, and then transpose the final result. Okay, so let's you may be thinking to yourself, what is the point of this? This is an awful convoluted mess. What value does this have? Well, the next theorem shows you some of the value, hints at some of the value. Okay, so theorem, if A is an n by n matrix, A is an n by n matrix with adjoint A, then A times its adjoint is equal to the adjoint times A, which is equal to the determinant of A times the identity matrix. That's interesting. If I take a matrix A and I multiply it by its adjoint, it's almost an inverse for A. So the adjoint is almost, kind of think of it like almost. The adjoint is almost an inverse of A. Okay, that's very interesting. All right, so let's take a look at an example. We've got our example that we just worked out. So I've got A is equal to 1, 0, 1, 0, 2, 3, 0, 0, 1. And I calculated the adjoint in the last example, and we found that that was 2, 0, negative 2, 0, 1, negative 3, 0, 0, 2. All right, so we have that. What this theorem says is if I multiply these two matrices together, I'm going to get basically the identity times a scalar. And that scalar will be the determinant. Well, we know the determinant of A, right? It's 2, isn't it? We did this example earlier. We calculated the determinant of this. And you could see 1 times 2 times 1 is 2, right? It's the diagonal matrix. Okay, so let's try it. Let's multiply A times the adjoint. 1, 0, 1, 0, 2, 3, 0, 0, 1 times 2, 0, negative 2, 0, 1, negative 3, 0, 0, 2. Well, if you just go through this, you'll see it's 2 plus 0 plus 0, and then it's 0 plus 0 plus 0, and then it's negative 2 plus 0 plus 2, so 0 altogether. Okay, 0 plus 0 plus 0, and then 0 plus 2 plus 0, and then 0 minus 6 plus 6, so another 0 there, and then you can see where this is heading, right? 0, 0, 2, right? Which is equal to 2 times 1, 0, 0, 0, 1, 0, 0, 0, 1, which is the same thing as the determinant of A times the identity matrix. Fascinating. And it doesn't matter the order of the multiplication either. This would be the same results if you start with this product, that the adjoint times A. If you go in that direction, you get the same result. Very cool. Very, very cool. Okay. All right, good. For the next item, I'm actually gonna kind of set up the demonstration ahead of time, and we'll land on the statement itself. So start with this idea of a matrix A with the determinant being non-zero. Okay, and so we saw previously in the previous theorem, literally we had that A times the adjunct of A is equal to the adjunct of A times A, which is equal to the determinant of A times the identity. Okay, and so in addition, we're going to assume that the determinant is non-zero. Okay, so because the determinant is non-zero, we can divide. So divide by the determinant of A. What do we get? Well, you'll get 1 over the determinant of A times, and I'm just going to use this one here. This is the easiest one to work with. We'll start with this one. So times A adjoint, and that's going to be equal to basically this guy here divided by the determinant of A, which is just going to be the identity, right? So you get this. And so this is just a scalar, right? 1 over the determinant of A is just a scalar, right? And so it follows that you would have this A times, so you can kind of move the scalar into the product here, and you can kind of think of it like this: 1 over the determinant of A times the adjoint, like so, and that's equal to the identity. Okay, so then basically what this shows, what does this show? It shows that the scalar multiple, 1 over the determinant of A, times the adjoint, that's got to be the inverse of A, right? So 1 over A times A adjoint is the inverse of A. Okay, this is just a very interesting way to calculate the inverse, right? So if you given a matrix A, if it has a non-zero determinant and it's easy to calculate the adjoint, then you can basically calculate the inverse in that way. Okay, so theorem, again, this is just the proof. We just went through the proof of this theorem, but if A is non-singular, then the inverse of A is equal to 1 over the determinant of A times the adjunct of A. Interesting. Interesting. Let's do an example. Let's do an example of this. We'll just work with our same matrix. A equals 1, 0, 1, 0, 2, 3, 0, 0, 1. Okay, from the previous example, right? This is the same matrix. So let's see here. So what we're saying is that A inverse is equal to 1 over the determinant of A times the adjoint of A. Well, we know what these matrices are. We've calculated the adjoint previously. It was 2, 0, negative 2, 0, 1, negative 3, and then 0, 0, 2. And so that was the adjoint previously. And so just plugging, and we know that the determinant of A is 2. We calculated that previously as well. So let's just combine these two and see if it does indeed produce an inverse. So 1 over 2 times this matrix, 2, 0, negative 2, 0, 1, negative 3, 0, 0, 2. And you get 1, 0, negative 1, 0, 1 half, negative 3 halves, and then 0, 0, 1. Okay, and so we're saying this is the inverse of this matrix. How can we test that? Well, we could multiply them together and see if we get an identity matrix. So A times A inverse. Let's multiply those together and check it. 1, 0, 1, 0, 2, 3, 0, 0, 1. and then 1, 0, -1, 0, 1/2, -3/2, 0, 0, 1. Multiply those together. And I will leave it up to you, but you do indeed get the identity matrix. Okay. Excellent. Excellent. All right, one last topic here, and this is a topic that you could spend a lot of time on. Unfortunately, you know, linear algebra being the subject that it is, full of interesting topics. This is one that I just want to point out, and I will leave it up to you guys to prove the thing and also work through additional examples. We'll do one example. But here's the theorem, and it's called Cramer's rule. Basically, the idea here is to use a series of determinants to calculate the solution of a particular kind of system of linear equations. So let's see how it works. Let ax equal b be a system of n equations and n variables. Okay, and I'll say with the determinant of a non-zero. Right, so we need non-zero determinants for the coefficient matrix A. So then for 1 less than or equal to I less than or equal to n, we're going to let AI denote the n by n matrix. We're going to let A sub I be the n by n matrix obtained by replacing the ith column of A with B. Okay, so I've got a coefficient matrix A, it's n by n, and I've got an n by 1 scalar matrix here, which is called B. So the system is going to be solved using a series of matrices A sub I, where A sub I is basically the coefficient matrix where I've deleted the ith column and I've plugged in B in its place. Okay, so I should have n of these matrices, A sub 1, A sub 2, da da da, A sub n. Okay, and each of these is characterized by being just the coefficient matrix, but with the ith column replaced by the scalar matrix B. Okay, and if I do this, then the entries of the unique solution X are, here they are. The first entry will be the determinant of A sub 1 divided by the determinant of A. The second entry will be the determinant of A sub 2 divided by the determinant of A, dot, dot, dot. The nth entry will be the determinant of A sub n divided by the determinant of A. Crazy. Fast. That's very strange indeed. And you'll have to think through why that would possibly be the case, right? But basically, solving this system boils down to calculating n plus 1 determinants. Right, so if it happens to be the case, you look at the system and you say, oh, geez, I can read off these determinants so easily. Then you can solve the system just using this technique. Now, it may or may not be easier to calculate n plus 1 determinants. It may be easier to row reduce it and do it the old-fashioned way. But it kind of depends. So this just, I mean, we bring this up not necessarily because this is the way to do it, but it's fascinating that this works. So let's do an example. Let's see an example. So let's consider the system. Okay, so 5x1 minus 3x2 minus 10x3 equals negative 9. 2x1 plus 2x2 minus 3x3 equals 4. And then negative 3x1 minus x2 plus 5x3 equals negative 1. So this is your system. Right, and from this we can extract the coefficient matrix A and the scalar matrix B. So A is just going to be 5, negative 3, negative 10, 2, 2, negative 3, negative 3, negative 1, 5. And B, of course, are these guys over here, negative 9, 4, negative 1. Okay, and so given the system, we can easily do this part of it. Now, what comes next here is we need to calculate A1, A sub 1, A sub 2, A sub 3. So the three changed matrices, right? So A sub 1, right? Remember, that's just the coefficient matrix where we've deleted the first column and plugged in B instead. So it'll just be negative 9, 4, 1, but then it's the same two rows as before. Negative 3, 2, negative 1, negative 10, negative 3, 5. So remember, this is the row that's different. In A2, it's the same operation, 5, 2, negative 3, negative 10, negative 3, 5, but the middle row is gone now and changed for B, swapped out. Okay, and then the A3 is the same, except it's the third column. 5, negative 3, 2, 2, negative 3, negative 1, and then negative 9, 4, negative 1. Okay, and so you can see here, right? So very easy to remember this. And now all we have to do is calculate all these determinants and do some division. And so I've done this work ahead of time, and I'll just tell you the answers and you can confirm on your own. The determinant of A is negative 2. The determinant of A1, A2, and A3, those determinants are 8, negative 6, and 4. Okay, and so that's just a matter of going through these and figuring out how you want to calculate these determinants. In this case, these are not like super easy to calculate, so it might take a little bit of effort. But once you have these, then the solution of the system is found by just doing the division. So it's A1 over A, which is 8 over negative 2. That's x1. That's the first entry of the x matrix. x2 is equal to negative 6 over negative 2, which is 3. And x3 is equal to 4 over negative 2, which is negative 2. Right, and so this is your unique solution to this system. Excellent. All right, very good. That is everything I wanted to cover in this section. Coming up next, we'll get into eigenvalues, and so that'll be sort of the last section for determinants. So we'll come back to eigenvalues later, but we're going to introduce eigenvalues and also introduce the idea of diagonalization of a matrix, how to take a matrix and diagonalize it, right? And so we'll talk about what that means next time. All right, until then, everybody take care, and we'll talk to you later.